I don't know, or we could wait 5 minutes or something like this if someone is coming or. And
Okay.
can you hear me well?
Yes, it is good. It is good.
Perfect.
Okay, now I think we are 14. I don't know, we can start or we can
Yes,
wait
I think
for
that
the
we
other
can start.
members. Okay, okay, welcome everyone to the first OBERON PhD talk that will be held from now on. I hope all of you are fine with your PhD and with your life. And I should say that Happy New Year for Iranian members of OBERON, and also Happy Spring for all of you. Today we have Iñaki here, Iñaki Blanco Martínez, one of the PhD students of OBERON. He is the PhD student of University of Minho, Portugal, and a bit about the background of him. I should say that he studies his bachelor on physics in the field of optics. And then he decided to continue his master at the field of physics and technology of lasers. Okay, today he wants to talk about off-axis wavefront model of the young aging human eye. And okay, if you are ready, Iñaki, we are here, and we are looking forward to listen to your attractive presentation.
Okay, thank you very much for the introduction. The presentation is going to be about the fundamentals of optics. It is the Optics 101. And I'm going to try to share my screen. Okay, I don't know if you're able to see it properly.
Yes, it is good.
Okay, perfect.
If you remember or something.
So as I said, okay, with this presentation, I have made it having in mind that people without any knowledge in optics. So this is going to be something more like a divulgative talk, more or less, in which my main goal is to try to explain you some concepts that I feel that they can be useful for the next presentations about visual optics or aberrations, and any other optic talk related to optics. So I would like to start showing this typical anatomical model of the human eye. We all know here about its complexity, but if we are working with optics, optics is going to be the branch of science or the branch of physics that is going to study the properties on the behavior of light. So we are going to be focused into the different elements that are going to be affecting the propagation or interacting with the light. Those elements are going to be, for example, anterior and posterior surfaces of the cornea and crystalline lenses, the pupil, retina, and the different media between them. So with this knowledge and a model as simple as this one, for example, we are going to be able to have a good intuition of how is going to be the propagation of the light or this pencil of lights on the human eye, for example. So what I would like to show you or to explain in this presentation is to explain some concepts as, for example, what are these rays that we are drawing, these indexes that can appear here, or how is going to be the behavior of the light when it finds different kind of surfaces. So I would like to start talking about rays and wavefronts. So now imagine that we have a source that is emitting radiation in different directions. So you can modelize, or you can, with some parameters, this radiation, you can draw it as a sinusoidal wave, and you're going to characterize this radiation, for example, with the distance between between two maxima. This is going to be called the wavelength, and we can define the frequency. For example, this is going to be the amount of maxima that you can find on a fixed period of time, for example, of 1 second. So they are going to be related, because if you want to have a higher frequency, this means that you are going to have a higher number of maxima on that period of time. So your wavelength needs to be smaller, and the opposite is true. Here, what I'm showing to you is what it is called the electromagnetic spectrum. And you can see that the different radiation, X-rays, ultraviolet, infrared, and microwaves are going to be characterized by the wavelength or the frequency. Here we can see that the visible light is only going to be in a small region of this electromagnetic spectrum. So now imagine that we are radiating this visible light. There is an easier way to represent these waves, and it is, for example, with these rays. These rays are going to give us information about the direction of the propagation of this portion of radiation. And now you're going to be able to draw these kind of surfaces. Imagine that this is an ideal media and we are radiating in all directions. These surfaces are going to be defined as surfaces are lines of continuous phase. This phase means that the distance between this point and the source is going to be the same as this point and the source. And you can define as much surfaces as you want. And in this case, those surfaces are going to be the wavefront. Now you can define this radiation of this source in all directions as, for example, these spherical wavefronts. There are going to be properties between rays and wavefronts, as for example, as I said, these rays are going to show us the direction of travel of a part of a wave. Wavefronts are lines of continuous phase, and these rays are going to be perpendicular to wavefronts. I said you that the distance between this point and the source is going to be the same as this distance between the point and the source, but it is not exactly the distance that you can measure in the laboratory. This is going to be called the optical path length, and it is the distance that you can measure by taking into account the index of refraction, taking into account the properties of the media. This index of refraction is going to give you information about the velocity of the propagation of the light in that medium. So you are going to be able to define it as the velocity in vacuum. This is going to be the highest one divided by the velocity in medium. So this is going to be usually defined between 1 and higher values. So now imagine that we have a source that it is emitting radiation in all directions, and you want to put an optical element here. If you are working in a region that it is far away enough or a region that it is small enough, you are going to be able to make the next approximation. This is a spherical wavefront, but in this small region, you are going to be able to approximate it to a plane wavefront. This plane wave is going to be quite useful for some calculations or demonstrations in optics. And the example is quite the same as in the case of the Earth, in which you feel that you're on a plane, but this is because you're in a region small enough that you can ignore the radius of curvature. So now imagine that we are going to analyze how is going to be the propagation of this radiation from one media to the another one. We know that the indexes are going to be different, so the velocity of the propagation is going to be different. So in a fixed period of time, it is expected to be different distances in this medium than in this one. Now we can see with the draw that there is going to be a change of the direction of the propagation of this radiation. So now we are going to try to find a relationship between this change on the direction of the propagation and the properties of the medium. We are going to start trying to calculate these distances. The distance, as we know, is the velocity of the propagation of the light multiplied by that period of time. And we know that there is a relationship between this velocity and the index of refraction and the velocity in vacuum. So we make the substitution and we get these two values for the distances. We are going to be using it in a few seconds. And here now, okay, we now draw a normal line to the surface. So what we want to try to find is a relationship between these both angles and the properties of the media. It's easy to see that, for example, in this case, by trigonometry, this angle is going to be the same as this one, and this angle equal to this other angle. So we have two triangles, quite easy to see that the sinus of this angle is going to be equal to this distance divided by AB, or the sinus of this angle equal to this distance divided by BC. So we can see here, and we are now trying to find, we're going to try to find a relationship between AB and BC. We can see here that in this case, this angle is going to be the same as this angle because it's the same radiation in the same media, and that this distance is going to be the same as this other distance. So if this angle is the same as this one, and this distance is going to be the same as this one, it's quite easy to see that AB needs to be equal to BC. So we make the substitution and we get this relationship. Okay, we have calculated D1 and D2, we introduce that values and we get this relationship. Okay, this is going to be one of the most important one in optics if you want to study the propagation of the light, and it is going to be called the Snell-Descartes law of refraction. So now you are going to be able to calculate how is going to be this angle. This is going to be the angle of refraction. So you are going to have an incident ray and a refracted one. So if you know the value of the indexes of refraction and the angle with which you are hitting this surface, you are going to be able to calculate this angle of refraction. We should not forget that there is going to be another ray, the reflected one. It is quite easy to see that the angle is going to be the same as in the incident ray, but in this case with a minus. The minus is because you are going to measure the angle from the normal to the ray. So this is going to be a counterclock angle, and this is going to be the opposite. And now that we know how is going to be the behavior of this portion of radiation in case of refraction and reflection, we could see a little example. In this case, if we want to study how is going to be the propagation by the anterior surface of the cornea, now I'm going to show you some examples or some demonstrations, little demonstrations. I don't want you to be focused exactly on those demonstrations. I only want to show you that with a few equations, you can have a good intuition of how is going to be this propagation, okay? So now we can see we have this surface, we draw this normal to the surface, having into account the height at which this ray hit this surface, and now we are going to have the angle with which is hitting this surface of incident and the refractive one. It's quite easy to apply the Snell-Descartes law, and it's quite easy to see that this angle is going to be the sum of this and this other. Now we are going to try to find a relationship. Instead of having into account these angles with the normal of the surface, we're going to try to find the relationship with this angle with reference to this line. This line is going to be parallel to this other, and this other is going to be called the optical axis of your optical system. The optical axis is the one in which you have this rotational symmetry of all of your system, and it's going to pass through a different center of curvature of the different surfaces. So now you're going to try to find a relationship with these both angles. Now we know by trigonometry that this angle is going to be the same as this one, so the sinus is going to be equal to y divided by r. So to the height at which you hit the surface divided by the radius of curvature. So if you apply now this series of Taylor, it is nothing more than that you can express a function as a sum, as a linear combination of other functions. And if you are working with an angle small enough, you are going to be able to be working like with this approximation, the sinus of the angle equal to the angle. This is going to be called the paraxial region, and is one of the most important and interesting in optics, because with this paraxial region, all of your calculations becomes easier. So we make the approximation. This is the shape of the Snell-Descartes law in the paraxial region, and we make the substitution in these equations, and we get now one of the first, the paraxial ray tracing equations, with which you are going to have an intuition of how is going to be the refraction in that first surface. If you know how is going to, what is the index of refraction of both media, the angle with respect to the optical axis that you are hitting that surface, the height at which you are going to hit this surface, and the radius of curvature of the surface, you are going to be able to calculate this new angle. But now you need to calculate how is going to be the propagation from one surface to another one. This draw should not be like this, should be with the lines, in this case in the apex of the surfaces, but I draw it in this way to make it more easy to understand or to see it. But we only with seeing that the tangent of this angle is going to be equal, not exactly to this height, should be to this height, but more or less equal to this height, divided by t. T is going to be the distance between both surfaces, and having in mind by trigonometry that the tangent is equal to the sinus divided by cosinus, if we apply again that we are working in paraxial region, the sinus will be equal to the angle, the cosinus equal to 1, so the tangent equal to the angle divided by 1. So the tangent is going to be equal to the angle equal to this height divided by the distance. This height is going to be equal to the difference between this height that we have here and this one, the one with which we are hitting the second surface minus the one that we are hitting the first surface. So now we have the second paraxial ray tracing equation. So now we are able to understand what is going to be the height at which you are going to hit the second surface, having the information of the first surface, this angle of refraction with respect to the optical axis, and the distance between both surfaces. And now you are going to be able to say, okay, I'm going to have an intuition of how is going to be the propagation of a parallel ray that I send to this easy model of the human eye. So if you send it now, you're going to know that you're going to have a refraction and a transmission from the anterior surface of the cornea to the posterior one, another refraction and transmission to the anterior surface of the crystalline lenses, another refraction and transmission to the posterior one, and finally another refraction and transmission to the retina. Okay, we can do it with different angles and you will get the same results. Okay, we are working now with what it is called of geometrical optics, because with geometry you can have a good intuition of how is going to be the propagation and the properties of the light in the propagation of this system. But we should not forget that we are working with waves, with these wavefronts, and if you put an optical element, this is going to be called a divergent wavefront. With this optical element, you're going to change the optical path, and you're going to change the velocity of the propagation, and it is going to go from a divergent wavefront to a converging one. So all of this radiation is going to converge to one point. This point is going to be called the image of your source. The source is going to be called the object. You're going to have the object plane, and now with these ideas that I have shown you, you can represent this radiation with different rays. Okay, if this is an ideal scenario, what we are going to recover is from one point another point, but this is only going to be in an ideal way, because now what I'm going to try to show you is some kind of phenomena that can appear related to optics that are going to make that you're not going to be able to have this punctual relationship anymore. First of all, I would like to talk about diffraction. Imagine that we have this source that it is emitting radiation in all directions. You have these spherical wavefronts, but now if you put an aperture, like for example in the case of the human eye, the pupil, you are going to be limiting the amount of radiation that goes through this aperture, okay, through this point. But now if you see how is going to be the image of this point, it is not going to be a point anymore. Now it is going to be an extended source. There is an extended image. Now there is all of a theory related to waves optics and related to the theory of diffraction that can explain this. But I think that with the principle of reversibility of Helmholtz, it's a good intuitive way to see why it should not be expected to have from one point another point. And it is because if you want to recover all of this information, you should need to take all of these spherical wavefronts to one point to the other one. But if you are putting this aperture, now what you are going to do is to recover the image of a wavefront segment, not of all of this spherical wavefront. And the source associated to that segment of wavefront is going to be an extended one. So the image of that wavefront segment is going to be an extended image. So you're not going to be able to be working with this ideal point anymore, and you will have patterns like this one. This pattern is going to be dependent on the wavelength of your radiation, on the shape of the aperture, and the size of the aperture. I would like to show you here an example that there is another phenomena related with this diffraction. It is going to be that theoretically in this aperture, the different points of this aperture are going to start to send different wavefronts as a secondary emitters, and these wavefronts are going to start to interact one with each other. So in this region that we can see here, this interaction is going to be what it is called a constructive interaction. A minima is going to find a minima, a maxima is going to find another maxima, and then your final wave is going to be a wave but with higher amplitude. So this is going to be a region with maxima. You have here another maxima but with lower amplitude. And then there are going to be other regions in which you are going to have destructive interaction. This destructive interaction is going to be that the minima find a maxima and a maxima find a minima. So the total energy is going to be pretty near to zero. So the distribution will be something like this function with minima, with maxima, minima, maxima, minima, with less and less amplitude, a sinc function. And in order to see how it's going to be in the case of a circular aperture, it's going to be quite similar, not exactly the same function, but we can see this distribution with this maxima, minima, maxima, minima. Okay, I would like to show you some examples with a laser going through a circular aperture. We can see that this will be the diffractive pattern with a lot of diffraction, okay? And now there is the dependence with the shape of the aperture. We can see that for a single slit, we have this distribution of maxima, minima, maxima, but with different apertures, we have different distributions. Here we have associated with a circular aperture, as in the case of the human eye, but it should not be expected this amount of diffraction. Okay, I would like to show you an example. I don't know if you have seen these images from the James Webb Telescope. If you see this bright object, this shape that we can see here, I don't know if it reminds you to something. It is quite similar to this distribution, so it should not be crazy to think that in the James Webb Telescope there should be some kind of hexagonal shape. So if you see an image of how are the plates of the mirrors of the James Webb Telescope, this is going to be a phenomena because of diffraction and because of the shape of those mirrors. I would like to talk about another phenomena, dispersion. Okay, we know that because of the Snell-Descartes law of refraction, now we have a relationship between the index of refraction and the angle of refraction, but now imagine that there is a relationship between the index and the wavelength. Now you're going to have a relationship between the angle and the wavelength. This is what is going to be happening if you hit with white light from one media to another one. The different colors, the different wavelengths are going to have different angles of refraction. This is going to be the typical example with the prism, in which typical album of Pink Floyd and so on, in which you can see that the refraction is going to be different for the different wavelengths. This is something that is going to be happening in the human eye. And for example, I didn't say, but if you have parallel ray to the optical axis, when it passes through your optical system, there is going to be one point at which it cut the optical axis. This is going to be called the focus of your optical system. So now, because of this dispersion, you're going to have different focus associated to different wavelengths, for example. So now one letter with white light is going to be focused in different points in the retina. And this is going to be the same phenomena as, I don't know if you have seen in a rainy day a rainbow. It is going to be because of this dispersion, because the sunlight is going to hit the water droplet. So you are going to have one refraction, reflection, and another refraction, but with different angles associated to different wavelengths. So you are going to be able to see, if you have the distribution of water droplets in this way, the different angles are going to be associated with different colors, with different refraction associated to different wavelengths. In this way, you will have here the green, the blue, and so on. So you will be able to see the rainbow. And this shape is because of the relative angle with the sun. There is another phenomenon interesting in optics, and this is going to be happening in the human eye. It's going to be called the scattering. If you have a smooth surface, the reflection is going to be quite perfect, okay? But if you have a rough surface, if it is not smooth anymore, you're going to have some kind of random reflections that are going to start to have different interaction of portions of radiation. So these interactions are going to produce commonly interferences, and you are going to get some noisy pattern as this one. It is called a speckle, for example, and you have that the different bright points are associated with constructive interaction, the black one associated with the destructive one. Okay, but there are other kind of scattering, for example, related to the particles that are on the media. For example, if we suppose that we are working with the vitreous and we have different particles on the vitreous, the propagation of the light, what it is going to be happening, that it is going to start to interact with those particles, are going to start to send with quite random reflection in rays to different directions. And what it is going to be happening is that the main source of radiation, the main beam, is going to start to lose energy and intensity, and you're going to start to introduce some kind of noise in the retina because of these different rays that are going to be at different random directions. But this is going to be the explanation, this scattering of this phenomena that we can see when we see to the sky. We are seeing the sky blue, but this is because the most scattered wavelength of the sunlight in the atmosphere is going to be the blue one. So when the sun is propagating through the sky, the blue contribution, the blue wave, is going to start to be sent in different directions. That's why you're going to see it blue, and it is the same reason why you're going to see it between red, yellow, and yes, an orange color. But this is because the sun is going to be lower. This lower position is going to be that associated to a region of highest density of the atmosphere. So you are going to have the highest values of scattering of the blue and green light. So now what you're going to be happening, and the distance is going to be higher. So now what are you going to have is that you're going to start losing that contribution of the blue-green radiation. So you're going to see it in this yellow, orange, and red color. And I would like to show this image only to introduce the last phenomena or property of the light. It is going to be that associated with the polarization. Here we can see the image with a polarizer in an objective or without. You can see that with a polarizer it is going to be more blue than without. This is going to be because the scattered light is going to have a polarization. So if you put a polarizer, you're going to be receiving a highest contribution of that scattered light. That is going to be the highest contribution of the blue one. So talking about polarization, I said you that you can modelize the radiation of the light as a wave, but this is what it is called an electromagnetic wave. This electromagnetic wave is an electric field oscillating perpendicular to a magnetic field. So if we are focusing to the electric field and we are focusing to the direction of the oscillation of this electric field, this is going to be the polarization. In this case, we can see it goes from bottom top in this way, in a linear way. So we will say that this beam is linearly polarized, but there are other kinds, as circular, for example, or elliptical. And I would like to introduce, I have been talking about ideal medias every time, but there are some medias, for example, called anisotropic medias that have some kind of phenomena, as for example, Birrefringence, in which the index of refraction is going to be dependent of the polarization of your beam. So you are going to have different indexes of refraction associated to different polarizations. So you are going to see that this beam is going to be divided in other beams with other angles. As this is going to be the case, if you see it here, the image is going to be duplicated. But this is because of this birrefringence of this material that you're going to see duplicated this image. And I'm showing this effect because it's something that we can find in the human eye, for example, in the cornea. As I read some papers in which they thought that we have birrefringence in the cornea, and this is because of the distribution of the fibers of the collagen in the stroma. Okay, and now I would like to give you an overview about different points that we have seen in this talk. First of all, wavefronts. These wavefronts are this line of continuous phase in which this distance, this optical path from the different points to the source is going to be the same. And now we introduce that this optical path is going to be related with the real distance and a new magnitude called the refractive index. The refractive index is going to give you information about the velocity of the propagation of the light in that media. So now you are going to be able to characterize different materials of different medias with the index of refraction, the ray propagation. So now you have an idea of how it's going to be the refraction on different surfaces and the transmission to the next surfaces. And this, because of this refraction, these surfaces used to be called refractive surfaces. But now everything is not as an ideal, as I said, because we have phenomena such as diffraction, for example, because in our case of the pupil, in which it is controlling the amount of light that goes to the retina, and because of this circular shape, you can have different patterns because of these wavefronts that are going to be emitted, that are going to be interacting one with each other, and you're going to have this kind of patterns because of interferences. I talk about dispersion, so this property in which the index of refraction has a relationship with the wavelength, so you are going to have different angles of refraction associated to different wavelengths. The scattering, because of, for example, different rugosities of the surfaces of different particles in the mediums. So this is going to start to emit radiation in different directions, introducing quite noise in the retina. And for example, you are going to start to lose intensity or energy of your main radiation. So this is going to be a problem, for example, for the process of the information in the retina, because you're sending less and less information. And finally, about polarization. If we are focusing to the electric field, we know that the light is going to be an electromagnetic wave. So if we are focusing to the direction of the oscillation of the electric field, we will be talking about the polarization of the wave. And there are some materials that depends on the polarization of your beam, as for example, in the case of the cornea with the birrefringence. And I would like to say that in the next talk, I will speak about aberrations. Now that we know what's a wavefront, these aberrations are going to be the difference between this ideal wavefront and the real one. They are going to be divided into different groups, as for example, the spherical aberration, coma, stigmatism, curvature of field, and distortion. They are going to affect what is called the optical quality. So I hope to have enough time to talk about the optical quality in the next talk. And I hope that you have enjoyed this little first talk. And I only have to say that thank you very much for your attention.
Okay, thank you so much, Iñaki, for your attractive presentation. It was very
welcome.
Nice. If anyone has any can ask Iñaki. We are waiting.
Well, I want to thank also Iñaki for this introduction. Has talked very, very fast, but very clear about the different phenomena that light can undergo when it interacts with matter, and giving an approach also on how this is present in the human eye. So, well, we are looking forward for the next one on aberrations. Well done, and well, hope that someone has some questions or additional inputs or some comments or criticism or anything. Thank you very much.
You're welcome. And I hope that you have enjoyed. Yes, of course.
I have a question. Can you hear me?
Yes.
Okay, it's just a simple one, just to understand, since I'm not from the optical field. But you showed really clearly some optical phenomena. And they were all, of course, they were let's say scheme, if I can say this, in 2D. But can you apply also to 3D models this kind of an optical analysis? I mean, instead of considering a 2D surface, extend a 2D line, let's say, extend it to a 3D surface, like, for example, the whole cornea. If there are any models that consider these optical characteristics in 3D. I don't know if this question makes sense, because yes. I work with 3D models, so I'm trying to find a connection.
That property is associated to the ray propagation. Of course, it can be applied in a 3D model without any problem. And the other phenomena, for example, diffraction, I'm not pretty sure, because this is more related with wave optics. The part associated with the ray propagations, I can see that it can be applied. The others, as I'm not working with, I'm not pretty sure if with geometrical optics there are some approximations, but I cannot answer you like yes exactly or not.
Okay, thank you.
You're welcome.
Benedetta, yeah, you can use ray tracing models, and some of these softwares, of course, they work on a 3D model, and you can combine the structural model with the optical simulations, and most of those softwares have a wave optics propagation platforms also. They usually show us rays, but they have also on the background other assumptions, not only geometrical optics, and some are specific for Gaussian beams propagations and more complex things related.
Yes.
But for the eye, it works reasonably well with this kind of CMAX, Code 5, Oslo. They are modelization softwares that work with ray tracing, and all that is in the background is in part what Iñaki has shown and will show on the next one on aberrations.
Yes.
I also take the opportunity to say hello to all the researchers, all the supervisors that are connected, and a special one, our external advisor, Professor Ray Applegate from the University of Houston. It's a pleasure to have you here.
Yes.
Thank you. One thing this is Ray Applegate. One thing I would offer that I think is that helps me visualize the 3D space is to talk about the tip and tilt of the surface at every location, and then applying Snell's law to that. And I think that will be particularly helpful going into looking at aberrations. And I find that very helpful in transferring information to students, is that if you picture very small areas of the surface having both tip and tilt, you can easily show that rays in different directions. And so what I find is students get very dependent on the periaxial approximations and quickly forget that you can do true ray tracing at every location by keeping track of the tip and tilt of the surface. And that little change in concept reminds the student that the periaxial equations work. They don't work very well when the pupil is large. Yeah.
Thank you very much.
Thank you, Ray. Great input. Thank you also to the Dissemination and Communication Committee with the head, Sabine Klein here. This is a great initiative. We are looking forward and very excited about the next sessions. Great initiative.
Okay, thank you so much, Jose, for your talk. I don't know if you have anyone else has any question. I think Fabian has a question.
Yeah. It's maybe not a question. Maybe it's some help for everyone that's not had optics before. I will send you some links of the sites that you can find the basic of optics that are really good, like SPIE or LP photonics, that you can find the really basic of everything.
Thank you very much, Fabian.
Okay, thank you so much, Fabian. If anyone else doesn't have any question, I want to be thankful again of Iñaki. It was very good and attractive presentation, and we are waiting for the next meeting. That I think it is going to be held on 29th of March, right?
Yes, that's it.
Okay. We are looking forward to listening to your attractive talk about aberration. Thank you so much.
You're welcome. And see you in the next one.
Thank you.
Thank you. Bye.
Thank you.
Bye.
Bye-bye.
Bye-bye.
Bye.
Bye.
Thank you, Iñaki.